I'm swirling around?
Yeah, I can see you.
Let me move that off. I'm not sure what Teams shows and what they don't show, so. All right. All right, Dipankar, are you ready?
Yes, you're ready to go. All good.
All right, let's do this. All right. Hey, everybody. My name is John King. I am a principal field architect here for Imply. For those who know, don't know, Imply is the enterprise arm of the Apache Druid project, and we were founded by the founders and the original creators of Druid. And what they realized was they needed the ability to effectively manage the cluster, manage large clusters, do visualizations, and do APM on those clusters. And so that's really where Imply came from. But what I really want to talk today about is Druid itself. And what we'll do, a little bit about me. I've been in big data for about 13 years now. I started in late 2007 with Hadoop. It was one of the very first Hadoop installs in the world. But through that, I've been able to work with lots of different technologies: data lakes, Hadoop, Hive, HBase, and now Druid. And through that journey, I've also had the ability to contribute and author a couple of O'Reilly books. So back in 2012, I worked with Ed Capriolo and Dean Wampler and Jason Ruthven on the Programming Hive book. And in 2019, I was able to write a book with Holden Ackerman on data lakes in the cloud. And that was shortly before I came over here to Imply and moved into more of like the real-time data space. So moving out of the data lakes and into the data rivers. So just a pretty brief about what we'll be talking about today is how do we go from data warehouses to data rivers? And I'll give an overview of like the progression of that and the architectures and how those have changed over the years. We'll talk a little bit about analytics problems at scale, and talking about what do people expect these days from their analytics applications, and how do we interface with people in real time and self-service data. And then we'll start the deep dive into Druid, and we'll talk everything from the architecture, what each of the pieces do, all the way down to the really nifty parts about how do we segment the files, and how do we store the data that makes it so fast. And finally, we'll talk about how you can try this at home. We have a really nice way of being able to download the distribution and run it on your local laptop. So, and this is meant to be interactive. So, please feel free to ask questions in line. I'll pause at certain times to ask for questions. But if you have a question, throw it in chat or ask in line. I don't want to be talking at you the whole time. That's kind of boring. But let's, if you have a question, let me know. All right, let's get rolling down the river. So let's go back to where it all began. And my son is a big fan of Aladdin, so I use some Aladdin. This is a little bit of Aladdin theme. If anybody works for Disney, I'm only stealing your content with the utmost respect. So where did we start? I started in data back in the mid 1990s, and this was the architecture that we typically used. We had data sources. It went through, this could have been like, COBOL programs, could have been through, nifty new web applications, MySQL, Postgres, things coming out of that. And that data was taken through ETL processing. So these were systems like Informatica, or people were designing systems in C and things like that, and moving that into a data warehouse. So moving it from a transactional system, OLTP, into a data warehouse type system. And, this could be Oracle. I think Oracle RAC was around at the time. Some of the early days like Ingress and things like that. And then finally getting that data out to your end users, whether it was for analytics or reporting or data mining, more along the querying phase. So what happened with the advent and the rise of the web? You know, data sources stayed the same, they just got bigger and they got more complex. So now we had, you know, instead of just a few MySQL machines or a few database machines or Oracle machines, right now we had these very large installs where it could have been hundreds or thousands of MySQL machines producing data coming in from web applications. It could be applications dumping data directly into, you know, a pipeline or things like that. JSON, the amount of data and the size of data and the types of data has just exploded, right? The ability to create data was now very easy to do, and people were taking advantage of this. So what did we do? It came down to the point where we couldn't load all this data into the traditional databases. Like, you know, we quickly swamped MySQL and Oracle and these. We had to be very judicious on what we loaded into those. So the easy answer was to, well, disk is getting cheaper. Let's dump it on cheap storage, and then we'll figure out what to do with it later. This is where MapReduce and Spark came along, and the ability to have, you know, distributed applications, get at your data in your data lake and to process that. You know, it was cumbersome, it was slow, but people didn't care. They were excited that they could actually get to their data and they could make sense of this vast amount of data, right? They had a whole data lake to them, right? And what we did is we used MapReduce and Spark as the ETL, and then we pushed that out to the to traditional SQL databases, MySQL. We stuck ML and AI on top of that, right? And then now we have this new breed of distributed databases, Cassandra and HBase and Elastic. And we use MapReduce and Spark and that paradigm to push data into that now. And now we could service customers in different ways, right? Elastic, very good at search. You know, HBase, key value stores. Cassandra, another key value store. So we could look up key and values very quickly. We could look up multiple documents by just a very simple asking it about like what terms and what terms were associated with these documents. Right? So the evolution of the evolution of these pipelines and the source systems grew very rapidly. What came out of this was, right, okay, so we had data lakes, but that still didn't absolve us from the fact that there are certain parts of data that, like certain streams of data or certain subsets of data that are very valuable to the business, right? It could be telemetry, it could be sales numbers, things like that. And these were all really important to the business, and people wanted to know about these very quickly. So we came up with the idea, is like, well, okay, well, how do we move data from A to B without this, you know, storing the data on disk and then having to ETL it? So this is where Kafka came out. And so now what we started to do is we moved data from the producers and we connected them directly up to these stream hubs. And then, but that didn't, we still needed ETL, right? So we needed the ability to take data, to obfuscate it, to enrich it, to hydrate it. And so we came up with stream processors, Kafka streaming, you know, Spark streaming, things like that. This is, you know, these were some of the very first ones. Now we have Flink and, you know, a whole slew of other ones. But really the idea is to process the data on the stream as it's coming in and to enrich it in less of a batch mode and more of an event by event mode. And now, instead of pushing this data out to these end systems, these end systems now can read data directly off the hub. And they can keep track of the assets themselves. So it can be a message by message ingest rather than a whole batch. Like, you don't have to load it every 24 hours. So the idea is really, you know, if we look at the core ideal of this, it's really to go from data to insight to action as soon as possible. So let me pause here. Does that make sense to everybody?
Yeah, definitely, John.
Okay.
It's very good, startup work. But we don't have any questions so far. But I'll report
Okay.
if there's any question, please feel free to ask.
All right. Right. So now these downstream applications, they can pull data in real time. They can, read it as fast as the Stream Hub can produce it. And so now, now we don't have these 24-hour lags. We can get data very, very fast. Additionally, this brought in the whole idea of, okay, well, what is streaming analytics? How do I make sense of all this data in motion? This is where KSQL and Druid really started to come out of. How do we ingest the data very, very quickly in milliseconds, and it's supposed to express that back out to end users. But this also brought on a few problems, right? How do we do slice and dice for big data streams? Like how do we query that efficiently and make it responsive to end users' application? How do we have interactive exploration where rather than going through data warehouses where you have just a few columns that have indexes on them, and you have to stay within those indexes, otherwise the the big bad DBA comes to your desk and says, I'm here because you broke something, right? You broke my database. How do we move beyond that? Additionally, dashboards are really good at knowing like what happened, but they're really terrible at telling you why it happened. So how do we look at the next level down of data? How do we do introspection into that data and figure out the why things happened, like correlations, or how do we even do simple things like understand a peak or a spike, right? Right. That depending on your data warehouse, it's really hard to do, right? That requires a lot of table scans, which generally aren't very good. And that gets you a visit from the DBA. I'm here because you broke the database. Additionally, right, before we had Hadoop, we just had data. There was so much data we were throwing away because we couldn't store that anywhere, right? And then we got data lakes and we got MapReduce, but MapReduce was cumbersome, right? And then we got Hive and it sped up a little bit. And now we have Spark and it sped up a little bit more. But there's still fundamental gaps in that cause data to be latent, right? You spill data to, you have to spill data to disk, and it's got to close out the file before you can read it, and that file could live, I don't know, for an hour, right? So there's always like some gap there that you have this data in flight, but you can't make any sense of it. But we all like instant gratification, and so it means that we want our data fresher. We want it more real time. How do we know what happened just a few seconds ago as opposed to a few hours or a few days ago? These are like some of the high level problems that we ran into when as data, the velocity increased, but yet the pressure to understand the data increased as well. Ultimately, it comes down to what end users want. For anybody that's been in analytics, when you take an analytics position, you usually get a screen and you get a computer, right? And then you get a data dictionary that's this big, but it's missing a lot of tribal information, right? And then you start writing SQL and it's like, oh, what was that join there? What was this? And the ramp is really, really slow. What people are expecting more now is data-driven applications, applications that are responsive, drag and drop just like this, that come back, in the speed of conversation of the data. And it's just the world we live in. we're getting asked to do more faster. And people are expecting more user-centric user experiences. Additionally, on the other side, like as administrators, what do we have to deal with, right? We have to deal with scale. What happens when data is large? We need a lot of servers. We need more budget, more CapEx, more OpEx. We're continually being asked to, how do we make the end users more responsive, right? How do we aim for sub-second response time so that we can service users, a lot of users, in concurrency very, very quickly? How do we deal with cardinality? How do we deal with complexity? Right? For a lot of us, we would try and pre-compute all those questions inside the pipeline, and then egress that data out to a downstream application. But what happens is the business changes, is the user question changes. What happens if somebody wants to do ad hoc analysis on their data, and it doesn't fit within those boxes? What do we do? Right? We have to go back all the way back up to the beginning of the pipeline and change everything all the way through that pipeline. And that can take, days, weeks, months. If you're a big financial firm and you have lots of data governance, it could take years. Pre-compute sounds good, and it works sometimes, but it becomes a hindrance when your business is trying to change. How do we deal with high dimensionality? Tens, hundreds, thousands of dimensions. Our phones, right? 5G. Like, if anybody's worked with any of the carriers, 5G emits like every second, data that's about 3,000 dimensions wide and has about another 2,000 metrics that goes along with it. Just huge amounts of data coming out of this one little phone here. Like, how do we deal with that? Concurrency. How do we deal with this as people come onto the system? And more tenants and more, how do we surface data internally and then externally for users, customers? How do we deal with that? And then additionally, how do we deal with loading data from streams very, very quickly as we move from the data lakes into this data river environment? Right, all the challenge. I mean, that's 6 challenges right there, and that's just scratching the surface. So a quick question, like, how many people deal with this, like, in your day-to-day data lives? Like, anybody deal with these ADBAs online? Yep. I'll assume that there are. So, what is Druid? Right? Druid is a hyper. Yeah.
Sorry. Yeah, I think John has a question. John, you can go ahead and ask.
Yeah.
Sorry, not really a question, because to answer John's question, you have to deal with all that.
Yep.
For sure, yes. Or at least some of them, right? Scalability and the low latency, that type of things when you deal with the IoT. IoT data streaming.
IoT, clickstream, anything, financial data. What happens when, how do you monitor a system rollout? How do you monitor a new software version rollout? Make sure that it's not impacting revenue and things like that. How do you know right away versus 24 hours or, heaven forbid, even a week, even a week ago? Some places take a week to get the data out, right? It's not easy.
Also, I'd like to add there, when I was saying like all the points you tossed, the challenges, because I've been working like last 13 years with the data warehouse. I know like how the data warehouse is like changing small things. I used to work in a company in the financial industry, and they had a timeline to just adding one column. I think they have estimated time for 2 days or 3 days, just whatever you would like to add. Think about those kind of things. It's challenge any changes.
Yep. Yeah. I worked for a big bank in the early 2000s, and I hate to say it, but I was part of. If anybody's seen The Big Short, I was a part of that, building the system, the trading systems, and things like that. So, financial systems, like I said, could take months or years to actually get a change in, if ever. really, really difficult. Yeah, any other questions or observations? No? Okay, cool. All right, so what is Druid? Druid is an open source project. It is a high performance analytics data store for event-driven data. And when you submitted a project to the Apache Foundation to become an open source project under the ASF, you have to give a description of what it is. And this is the one that we gave. So let's break it down. There's a few things behind this. High performance, like how do we have low query latency with high ingest rates? Usually in data warehouses, these compete for the same resources, right? How do we solve that? Analytics, like we're an analytics system, not a transactional system. It's an OLAP system. So counting, ranking, grouping by time trends, scans, things like that. Really, really great for that, but not so much on the update or the delete side. Druid is actually a data store. So it brings the data, it reads the data in batches from Kafka or Kinesis or a streaming application, or from local disk, right? Disks, remote storage. So things like HDFS or S3 or ADLS, Azure Data Lake, blob storage or GCS, things like that. The ability to bring in real-time and batch data at the same time is something that Druid does. But it brings it in, it optimizes it, stores it in its own file format on the data store. So it's actually a database. And if there's anything I can get through, make crystal clear is Druid is a database. And so when we talk about analytics in motion, we're not continually scanning over Kafka or Kinesis. We're actually taking the data off and converting that to a file format. And finally, it's about event-driven data. So fact data like clickstreams or network flows, user behavior, digital marketing, ad tech, server metrics, IoT, anything that's event-driven works really well inside of Druid. And so what does this new data architecture look like? And so this is kind of what we boiled it down to was, we talked about on the left-hand side there, you have data producers putting it to the stream hubs. You have stream processors, which are doing enrichment and hydration or obfuscation. And then it's pushing it in almost real time, probably within 50, 60 milliseconds to some type of analytical database like Druid, distributed database. Since we're here for Druid, we'll talk about Druid in this sense. And then having these interfaces, whether it's SQL or NoSQL, out to these new applications like Pivot, Apache Superset or Looker or Tableau, right? Being able to interface with multiple different applications, and it doesn't really matter which application you're interfacing with. What's really important is the speed and the scale of the analytical database in the middle to crunch through small or large amounts of data and provide users the ability to analyze the data and to move from raw data to, like I said, raw data to insight to action as soon as possible. And these analytical databases, right, they're serving multiple things now. And we'll talk about this about Druid is, ETL is kind of gone here, but how do you do aggregations? Like, how do you do rough cut aggregations if you need to? How do you merge an aggregation in a serving layer in something that's easy to use and but yet distributed, right? How do you hide the complexity of the end user or the end application in a very simple way? So a few key features about Druid. It's a column-oriented store. So like I said, it's not really, it's not transactional. We insert data, but we really don't ever expect to, like delete a row or update a row, right? Once that data lands, it's pretty, it should be immutable. Except in extreme circumstances like GDPR or CCPA, or if you have to obfuscate data, because of some regulatory compliance or something like that. The other side of it is, how do we handle high concurrency? So we all know that once people get access to the data, people are going to want more access to more data, and more people are going to want to hop on and get more access to data. So it's a self-feeding cycle. If you give people a good system that provides them with a great data experience, they're going to continually pile onto that. And how do you handle that concurrency as opposed to being a victim of your own success? Right? How do you scale out to hundreds of servers, or millions of messages per second, or even thousands of servers and tens of millions of messages per second? Right? How do you reduce the bottlenecks and design a system that can handle that? How do you have continuous real-time ingest with fault tolerance? We'll get into that in a little bit, but what happens if a task goes down, or how do I have multiple tasks reading off of the same data source, Kafka, but yet they're not processing the data twice, right? How do you do that? And this next one is what really breaks people. It was hard for me to, coming from data warehouse and Hadoop that didn't have any indexes, or data warehouses that had just a few indexes too. What happens if I turn indexing? What if I design a system that has indexes on all dimensions by default, right? What that means is, what if I index all of my data, and now I'm not afraid to do table scans, and I can use those indexes to my advantage? We'll talk about bitmap indexes and things like that here as we get into the deep dive shortly. Let me do a quick time check here. Cool. How do we query through SQL, right? SQL is the language of getting to data. If you've been in this industry long enough, you probably remember the days of NoSQL. SQL's dead, right? It's all about JSON objects and querying through APIs. Now what you see is, you see MongoDB, all these systems. Now the first question they ask is like, how much SQL do you support? Are you SQL 92 compliant? How SQL compliant are you? Because our users know SQL, they don't know JSON, right? So it's been this backtrack of moving from this, the war cry of NoSQL, back to SQL, because analysts, they like SQL, right? It's easy to use, and it's well supported and well documented. And then the final one, how do you ensure people have a great data experience? How do you ensure that people can have a conversation with the data? And I mean conversations, not in the Hadoop sense where, I would write a MapReduce job and then do my unit tests and then submit it, and then I go get coffee, right? Or I go to lunch and I come back a few hours later and maybe it worked, maybe it didn't. How do you have a conversation with your data, just like we're having a conversation right now, that people can respond in real time, right? Or how do you get queries to respond in sub-second to just a few seconds, right? At scale, while having massive amounts of ingest. How do you design that? These are all things that Druid, in its architecture, was built to solve. Let me pause here. Any questions?
I don't see any question. Anyone has? Yeah, John raised hand. Please go ahead, John.
Yeah,
I would like to know how the architecture looks like
Yep.
of the Druid. And you mentioned all these hundreds or thousands of servers. Is it more like a MPP architecture-wise?
Yeah.
Or it is?
Yeah, it's kind of like MPP. It's probably closer to distributed computing, where a shard of the data sits on a server,
Right.
and then a scatter gather and go get the rough cut of the data, bring it back, and then do the fine cut, and then return the results back to the end user.
Okay. So
Yep.
you expect the user to have all the partition
Nope.
configured? No?
Nope.
Okay.
Nope.
That's good. If you can write it efficiently without the
Yeah.
user's input on that front.
Yep.
That's
And so that's where I had talked about, like, how do you mask the complexity of a distributed application from the end users and
right.
make it simple. Like, that's the hard part. But we'll get to that here in just a second.
If we look at Redshift or the Azure SQL data warehouse, they all require you deep knowledge about your data so you can provide the proper partition scheme.
Mm-hmm. Yep. Right. Exactly.
Okay.
How do you make that really simple for end users and for, to be honest, administrators? Right. I kind of went over this. Use cases that work really well: clickstream, user behavior, digital advertising, network flows, IoT, things that are basically coming in on the stream or coming in a file, and you're not like going back and updating things. So storing users, passwords, things like that, not Druid's thing. Storing clicks from the user, storing event logs, things like that. Yes, totally right down Druid's wheelhouse. So we're really proud about the community we've built. You can see a lot of, all these companies here use Druid. There's one in the right-hand side, about halfway down, called MetaMarkets. That's where Druid was actually created. They're an advertising ad tech market. That's where it was created, but then it just kind of skyrocketed from there as people wanted to get into data rivers and get into real-time data, but to accelerate also their data lakes, things like that. So PayPal, Airbnb, Hulu. So it's a lot of logos here. So let's break it down. This is where these are like these are 6 channels, 6 verticals where, Apache Druid is really important to their business. So like retail, Walmart, what's going on with their sales, what products are selling, what categories. Walmart actually does A/B testing with their data. Like, some products they'll put in health and beauty, some they'll put in, other areas in different stores. They'll try A/B testing that way. Capital One, New York Stock Exchange, what's going on with the stock exchange in real time. Network, things like that. Yahoo, AT&T, communications. One of the fun ones, like how is our network performing, right? Do we have any degradations? How, do we have hotspots in some areas? Do we have downage, or do we have downlinks in other areas? That's a big part of what communications verticals use it for. In hospitality, Expedia, Airbnb, TravelClick. What are our users doing? What are they booking? What's our book rate? When COVID hit, right? How many people are canceling? Things like that. So being able to respond to, especially in the hospitality industry, being able to respond to COVID very quickly was what saved a lot of these companies. And having data that was low latency was really important to that. I like customer sentiments. This is from Yahoo, and they use Druid. when we were talking with them, like the performance is great. Imagine tables that have billions of rows in them and scanning those in under a second, right? Imagine that conversation that you can have with that data and how many cycles you can do with that data, right? How many queries you can run in a day. So that's pretty powerful. All right, so now we're starting a little bit about the deep dive into Druid. Right now, we'll get into more of the architecture piece. Druid was started in 2011, and by that time, a lot of these other databases had already existed. So, OLAP analytics for top in and group by and time series, right? Those are three different query styles, right? Column-oriented stores have been around for a long time. There was a lot of lot of good trailblazers that showed how to do OLAP analytics, right? But now you had things like time series databases that are partitioned by time, time bound, and grouping by time, doing things, grouping the data by time so that you could do file pruning, and use less resources during the search, right? And then search systems, right? Lucene was one of the first ones, in the open source world, and using inverted indexes. How do we look at terms and see how many documents were associated with those terms, and how do we go get those documents in an efficient manner, right? Dictionary encoding, how do we turn a string into a number, because computers are really fast at aggregating numbers. They're not really fast at aggregating strings, right? And then using bitmap indexes, things like that. So Druid, we bring in the best of breed of all those architectures and we use it within the system. All right, let's go to the deep dive here. We do a quick time check here. All right, right on time. All right, so here's the architecture of Druid. And so just like Hadoop and many other systems, we have a coordinator here. That's what's keeping track of all the files. The coordinator is also keeping track of which of the systems are alive, and making sure that the data is in the correct shape, replicated across the correct number of instances and services, right? So the coordinator really manages the data and where it lives. The overlord here, like, these are the two masters that basically manage the entire system. The overlord is responsible for any task that's happening on the system. So a task is typically associated with indexing the data, right? And so the overlord here is making sure that the indexers are running the correct tasks, the tasks are healthy. If the task isn't healthy, it basically kills off the task and tells it to restart in an HA and fault tolerant way, right? And then the indexers are bringing the data in. So, a system, a database is only good if you get data into it. So how do we get data in here? Well, the indexers will read data from either a file-based system. So like I said, S3, GCS, Azure Data Lake, NFS, things like that. Anywhere it can get access to the data, or it can connect up to streams. So things like Kinesis or Kafka or Azure Event Hub, right? If they can connect up to Azure Event Hub and read data in through those streams if you want data, more low latency data. But the cool thing here is it can read both of these and can bring data in to the same system and make sense of this, like, near-term hot data streams, as well as the long-term file data, right? So I'm not just limited to one type of bringing data in. I can get to both, data, whether it's in my data lake or if it's on the stream. And so back to John's question, How do you make that? Any questions?
Yeah, John, I think I have a question here.
Yeah.
So, as you mentioned, it's the event driven, right, Druid Is. So I'm just wondering, for example, I understood about the stream data, IoT or whatever is or API, but when it's come to the transaction, think about, okay, I have the data lake, but I would like to get the data when there is any record inserted into one of the transactional system, and then
Uh-huh.
I'd like to get the data immediately to my data lake, for example.
Yep.
How do you do that part?
So the real response is we don't manage that. There's a lot of other systems that are better at managing that, things like Airflow, or there's a lot of change data capture systems which are that can manage that, but those systems can also reach out to Druid and say, hey, there's been a change in this data, go grab it and go index it and merge it into your overall data set.
Okay.
Yep.
But as long as even there is a, for example, file, someone drop it, there is a changes, so the system generate that file. Okay, this is the record that has been added. That can be actually moved to Druid easily.
Yeah.
Okay.
Yep. So that there's a lot of systems out there that will watch the file system for new files or changes, whether it's based on M time or C time or things like that. Your typical POSIX file system metrics, and then it can decide. It can tell Druid to go get that data, and then Druid says, "Cool, I got it. I'll go get it. I index it. I bring it in and merge it into the overall data set."
Good. Thank you. Thanks.
Yep. Okay. So what happens so the indexers, think of that as like your near-term data, like your last hour worth of data. So this would be like your real-time. We also call this a real-time index. This is all in memory. It's basically the simplest way I can put it is a hash map, right? Of just data coming in, and then when it gets queried, we just read through the hash map and pull the data out. But what happens when it reaches past that hour? Well, we need some place that can store data as it moves from the hot data or the near-term data to more historical. Well, we call these historicals. And so the indexer says, the indexer will then create a file, and then it will tell the historical, like, hey, go load this file, and put that into your longer term storage. There's a few other steps that happen in there, but that's essentially the easy way of explaining how that works. And so the historical will store anything that's longer, can store any amount of data, whether it's from, the last hour all the way up to the last 10 years, right? So this is kind of that distributed storage that we were talking about earlier, where the data is sharded, everything's, the data is now in a file. It's historical indexes it. It knows where it is, and then it just manages it from that point. So the indexers, near-term data, historicals, long-term data, right? Deep storage is something that it's a copy of the database, the data. It's used to move data around and to store for disaster recovery. So like if a historical, we always store a copy of the data in deep storage. So if I lose a historical, these other historicals are then told to go load the data from deep storage, right? So it's a way of keeping data safe. And so think of it as another layer of storage for the data, and that happens automatically. So one of the questions was, how do I make it easy for the end user without them having to know if my data is in the indexers or if it's in the historical? Well, we have another service called Broker, and the broker is actually what received the queries, and the broker keeps track of the brokers keep track of where all of the data lives throughout the system. So This is the scatter gather part of it. So if I send a query to the broker then will query all of the indexers and all the historicals. The historicals and indexers will return an intermediate file or intermediate results back to the broker, and the broker will do the final merge and return that result to the end user. But to the end user, all they did was I submitted a SQL query to this thing right here, and I didn't see anything else of what happened behind the scenes. So very, like we were talking about, how do we make sure the user doesn't have to know where all the data is and have to code that into their queries, right? That's how we solve that. Let me pause here. Any questions?
No questions so far, John.
Okay. So these are basically the services that run Druid, right? The overlord manages tasks. Oh, yeah, I did put that screen in. So the coordinator manages segments and the distribution of that data across the system. The broker nodes route queries and merge results. The historical nodes are responsible for loading and serving of segment files and long-term data. The overlord is responsible for watching over and delegating tasks, indexing tasks, batch tasks, real-time index tasks, things like that, making sure that they're alive and working as they should. And then the middle manager and the indexer, right, those are the tasks that are bringing data in and serving the real-time queries for the brokers. Those are the 5 services that run Druid. Hopefully, hopefully I did a good job of explaining what they do. Any questions about those?
Yep, John, please go ahead. John
Okay.
got a question.
Oh yeah, John.
John. Yeah, I know.
Basically all these processes, right? It's supposed to be responsible to data ingestion, data processing, and the user's query. So when what about the writes? Are you still using the same mechanism as the others, like write-ahead logging approach?
Not really write-ahead logging. So this is where it differs a little bit. The indexers are keeping track of the data in their hash maps. It's an easy way to put it. And the historicals are keeping track of the actual files. So there's not really a write-ahead log here. Everything is either immutable here in the historicals or in memory here in the indexers. Now, if an indexer goes down, and this, I forgot to mention this. If I'm reading off of a stream, every message gets its own offset, its own ID, and the offsets are always incrementing. So the indexer keeps track of every offset for every message that's coming in. If that indexer dies, it knows where to go back to the last offset and grab the data and bring that data current. And it does it very, very quickly. So what
about the I need the data transformation, right? You have to write some either intermediate or final result for my, say, the analytics tools to visual. So.
Oh, right. Yeah, so that would be down here in the broker. So the broker is the one that's bringing in those intermediate files and then merging that and then the queries down here, that would be like your user-facing system.
You never store any final data sets or results?
We do have a bit of a cache, but it's a very small cache. Most of the heavy lifting is all being done between the historicals and the indexers, and probably mostly the historicals. But they're very, very fast. To give you an idea, it's about 4 gigs. We can read about 4 gigs per second per vCPU. So they're very, very fast at reading data. And so we don't have to store the intermediate. We really don't have to cache any of the files on the broker for subsequent queries.
Okay. Thanks.
There is one more question from. Sorry, I'm sorry.
That's okay.
You please go ahead, Samson.
Yeah. Hi, John. Good job so far. In the previous slides, you showed a Venn diagram where you had time series data warehouses.
Yep.
Those are, I mean, and then in the current slide, you have historicals. So I'm thinking the historicals here are representative of those Venn diagrams.
Yep. So the Venn diagram here, and we'll get to this here in a second, is actually what we use inside of our files. And so you're like 2 screens ahead of me.
Okay. All right.
Yeah.
Thank you.
Yeah. So those are the higher level services that run Druid that are responsible for data governance, data loading, and data querying, right? You know, where do we fit well? Slicing and dicing of very large data sets, right? Because the data is distributed across multiple machines. We can have multiple CPUs working on it at the same time. Real-time analysis back to the indexer, right? Being able to that data from the time it's read from the stream to the time it's in the indexer is somewhere between 60 and 150 milliseconds. So really, like literally faster than you can blink your eye. And you know, sub-second fast analytics, and we'll get to this here in a second, like how we achieve this. You know, being able to do BI analytics, unique visitors per hour, per day, retention analysis. There's several different data types that we use to achieve that. Root cause analysis, the ad hoc side of it, you know, web traffic analysis by times, things like that. All right, how does Druid actually store the data? At its heart, Druid is the file system is a time series. So we group data by the time that it occurred, and so each data source has its own lineage of files, and so we'll put a start and stop time on that file, right? Whether it's a day, an hour, a minute, a second, things like that. But for simplicity's sake, let's say that there's, you know, we're using day level grouping on this, right? So we will do our best effort. We will store all the data in files based on time, and that's because what we find is a lot of these data sets, people are saying, I want to know what happened in the last minute or the last hour or the last day, right? And what this does is it allows us with as we build these files out, as the data comes in, we build the files out. As the files reach a certain point, we will cut that file off and we'll create a new partition. So you'll see like partition 0 and partition 1 here as that data grows. What we use that for is file pruning. And the best performance you're ever going to get from a database is by not scanning the data you don't need to. So if I'm looking at data from, you know, I want to know about the last day's worth of data. I don't care about any other data except for that day's worth of data. So let's not scan the files we don't need to. So file partitioning or file pruning. And that happens for every single data source. So every data, like I said, every data source has its own lineage. Does that make sense so far?
Yep.
Okay, cool. It's usually the one I mess up on, but sounds good. So like I said, you know, the data is time partitioned. And as that data gets in, you know, as that data ages, you know, increases, as we start to get somewhere into the 700 megabyte to 1 gigabyte file, you know, file range, we'll cut that file off and we'll start a new one. so really, we don't store everything in one large file. We store the data across the system in multiple small files. That way, we can have a CPU working on multiple files at the same time. Or we can have multiple CPUs working on multiple files at the same time. Distributed computing. Okay, so what actually happens inside of those files, right? On the left-hand side here is what you would expect to see from like a row, a transactional system, or if I do select star from a table, right? I'm going to see a timestamp, and so that's where this timestamp, when it's defined, will put this data into a certain file based on that timestamp. We'll see a column with its values. We call those dimensions. We'll see, you can have any number of those. We may also have columns that we want to do some, aggregations on. So some mix, min, max, we want to do histograms on it, things like that. We call those metrics. But when I said that Druid basically turns everything into a number and then does analytics on those numbers, this is what I'm talking about here. So a column here, right? We want to use column encoding. And so what we're going to do is we're going to take each one of these values, we're going to put it into a dictionary object, and we're going to assign an ID to that. So I can see here my buddy Ben Hop is in 3 of these, but he only gets one entry here in the dictionary, and his ID is going to be 0. And as Andre comes in, as we see Andre, we'll query, does Andre already exist here? If he doesn't, we're going to assign him the next ID. And then Harry, and Harry gets 2, right? And then what we're going to do is we're going to convert that to column store. And so we'll define the column, and then for every row that's in that column for that file, we will put the IDs in there. So Ben will get the first 3, Andre will get the next 2, and then Harry will get he'll get the final. Sorry, the final element in that ID. Any questions here?
No questions.
Okay. Yep. So really, we're just column encoding the data and turning it into a number. Now each value is stored as a bitmap index, and I'll talk about that here in the next slide. And then indexes are compressed. So we create a bitmap index for all of the data, and that's I'll show you why here in just a second. But this is the OLAP, the column side of that Venn diagram. Hit the wrong button. All right, so bitmap indexes. Change it around a little bit. So now we're looking at artists here, Justin Bieber and Keisha and Selena Gomez, right? The table up top is what we would expect to see if I did select star from the table. But we want to store these in bitmap indexes because 1, they're really fast, 2, they're compressed, and 3, guess what? They're numbers. Again, we convert everything to a number, and we work really fast on numbers. So Justin's going to get his own bitmap index, and he's going to be in rows 0, 1, and 2, right? So we'll convert that to a bitmap index. Kesha is in position 3 and 4, so we'll denote that she's in 3 and 4, and Selena Gomez is in position 5, right? So we convert everything to 0s and 1s. So what does that mean? Now, for most analytics, people are just counting rows and counting the occurrences that are of the data, right? They're not actually doing a lot of like fine-grained analytics where they would actually have to open up the column and look at values. So here we're actually just counting how many 1s are if I want to say how many times do I see Justin Bieber in the data, right? It's going to go to the bitmap index and it's going to say how many ones are in this bitmap index for Justin. 3. Cool. Return 3. I don't have to open up any columns. That's one of the ways that we can speed up the queries, right? Same thing with Keisha and Selena, right? If we're just going to look for those particular ones, all we have to do is say, like how many ones do I see in this data set, right? And then return those to the return those intermediate results to the brokers, and the broker does the final aggregations. The other neat thing about this is now I can do differentials. So let's say I want to say Justin, I want to look at how many rows have Justin or Kesha. So I can merge these very quickly in the system and just do count how many times they occur in the final data set. You can also do, that's an OR, you can do an AND. So you can merge those together and then do the final counts as well. How many times, like here, how many rows were English and occurred in, I meant to say state, but that's California. So how many occurrences were in English and occurred in California? So right, it's very quick to do those merges and then get the final counts with them. Let me pause here. Any questions?
No questions so far. Sorry, that's my kid. No questions so far.
Okay, cool. Right, so bitmap indexes are pretty standard for most databases, and they're, we use them to kind of bypass opening up columns unless we really need to. So most of the queries are just counting how many times this thing occur within the data. Indexes are also compressed, and in Druid they're compressed with concise or roaring encoding. Concise used to be the default, and I think within the last 5 releases ago that we made roaring the default. So roaring's a little bit bigger, but it's also a lot faster. Going back to that new the new world pipeline, remember, where I said that systems were now having to do, they were having to merge in multiple functionalities, things like doing aggregations in line and things like that. Druid can store the full fidelity of the data, so every row being its own unique row inside of the data set. This is good if you're if you're doing click tracking and things like that. Not so good if you want to do things like what's my network doing, and the volumes of data that can come out of a network. So what Druid can do is Druid can, as the indexer is bringing the data in, it can roll the data up and auto summarize it, so that things like network, or if I don't need full row fidelity of the data, and I can get away with summarizing the data, but still get 90%, 90+% of the value of the data. Druid has the ability to bring that data in, squish it, and do things like, how many rows occurred in that time frame, how many, what was the sum of the added column, what was the sum of the deleted column, what was the min, maxes, and there's some other special storage formats that we use there, which I'll talk about in a second. So this can actually be a game changer, where you may not have been able to store your like your network data or things like that because of the velocity and the granularity in a traditional system. We see a lot of people like Charter, that are using this because they can do that roll up in real time, and they don't have to have massive amounts of hardware running these systems, running the overall data set. So let me pause here. Any questions about rollups or auto summarization?
No question, Jonathan. No. But I got it. I think, it seems like the rollup, what they do, even when I was working with the OLAP, it was Microsoft OLAP, it's similar. How do you do it? Yeah.
Yeah. It's it's a nice way to reduce the fidelity, but not reduce the overall value of the data. And then it helps in quite a few times. It actually helps manage the CapEx and OpEx control, and then it also gives your users a great, a better experience because you don't have to scan as much data.
Yeah, right.
Yeah. Okay, approximations. Most of the time in analytic systems, people aren't looking for exact results. So people aren't looking for, I don't need to know the exact number of users that visited this page on this day. Having some type of approximation with a known differential is good enough. And so this is one of the things that Druid does as well. So by default, everything runs as an approximation. And so rather than having to scan every single row, Druid can create, Druid can use approximations to speed up the end user experience. One of the ways that we do this is something called sketches. And sketches are unique data structures that have a few different ways of being built, but think of it this way. Let's say I want to know, user IDs of how many user IDs accessed, like let's say this is Spotify, right? How many users accessed Justin Bieber's landing page or Keisha's landing page or Miley Cyrus's, right? Again, going back to this idea of rollups, what if I didn't have to store a row for every user ID that came in, right? What if I could do something neat like a hyperlog log, or I could store that data in, this is a gross oversimplification of it, but what if I could store that in an array where I only had to store the unique user IDs? I didn't have to store every occurrence of them, right? So I could take this data, I could, if I'm rolling up data, I see a user ID come in, I could very quickly query the sketch or array. Does the user exist in there? No, cool, add it. If it does, cool, it's already there, throw it away. And then at query time, I only have to count the number of elements in that array. I don't have to go through every single user ID, right? I don't have to map every user ID and then reduce it and then look for distinct, do a distinct count on that. It's much faster just to throw them in an array. Does it exist? Does it not? And then just count the array when needed. Right. So that was a lot there for sketches in a very short amount of time. Let me pause here. Any questions or any questions you have about data sketches or kind of the idea that they the problem that they solve?
Any question, anyone? No, I don't see any, but yeah, I think I got it.
Yeah.
It's very helpful, You don't have to really go find out who's the user, then you count on it, but you have everything there, just, get the count.
Yeah. Don't count the user over and over and over again, right? Just count them once and then throw them in an array and then do a count on the array. That's really doing a disservice to what sketches are, but that's the simplest way that I can make sense of them in my head. But essentially, they are just unique values and being able to do counts on those values. Yep. So sketches have a few different ways that they're built. So Druid exposes a few different types of sketches, and each one of them are are valuable in their own for their use case. The first one and the most the one with the longest lineage is hyperlog log, or HLL. And again, the example that I gave of like how many user ID, how many users visited Justin Bieber's landing page or Keisha's or Miley Cyrus, right? This is where you would want to use something like that. I don't have to do any additional math on them. I'm just looking for distinct counts. So throw it in the sketch, count it once, and then during the query, make sure it's in there once. But when I query it, I'm just doing a count of how many elements are in that sketch, right? So this is an alternative to count distinct, which can be very expensive, especially if you're counting things over and over and over again, and then you have to reduce it down to their distinct. This is really why it was built and incorporated into the system, is to make those count distincts very, very fast. HLL is widely used in the big data space. Boy, I can remember back to
We lost John.
Yeah, seems like I thought it was from my side.
Okay.
Let's see for a few seconds.
Yeah, that's an interesting way to do the counting.
Yeah, I think it's good part is we almost cover a whole session. Luckily, it didn't happen halfway.
Yeah.
Okay, he's leaving now.
Rejoin.
Yeah, hopefully he'll join soon.
Now he know he lost the connection.
True.
Is he doing this locally from Toronto?
Oh, this session?
Yeah.
Oh yeah, we are from Toronto.
No, he.
Oh no, he's from Colorado, I believe, from US.
Oh, okay.
Yes.
Okay.
Okay. Are you able to ping him or no?
No, on LinkedIn. But I think
Okay.
Sarkia, do you have direct contact?
Yeah, I'm trying. And in the meantime,
let me
Yeah,
ping him over.
he's there.
Over.
He's there.
Yeah.
Okay.
Hey everyone, sorry about that.
No worries.
No problem.
I'm not sure what happened, but he just got me back in, so that's good. Let's see.
Okay.
All right. Can everybody see me again?
Yeah.
All right.
Yes.
Turn camera back on. Cool. Awesome. Where did I bonk out?
You are here actually. Hyperlog. You're talking about exactly about this slide.
Yeah. So just to retrace my steps a little bit. So HLO was built to counteract the slow count distincts, because count distincts you have to count everything over and over again, then reduce them, and then sort them, and then reduce them to their individual values. So why not just throw something onto the sketch, make sure it's there once. If you see it again, just throw it away, because like your query pattern doesn't really care about how many times that user was there. It just wants to know if it was there. So these sketches are really, really small. They're faster and they're pretty accurate. But when we talk about approximations, we want to know what's my confidence level, right? And we've done a lot of iterations in Druid to give the right like LGKs, the right settings for the right confidence level. So these are all tunable if you want to use sketches. So depending on what your error rate is, you know, you can see like one standard deviation about 1.63%, two standard deviations 3.25, you know, up to a max of about 5%. So you can use approximations if you don't have to have 100% confidence in your, you know, 100% counting in your results. You can turn it off and do full counts, but the query is going to be a little bit slower. But for general analytics and trolling through data and just getting an idea of like what's, you know, what's 95% of the data say, you know, approximations are good. I would not use approximations for any financial applications, obviously. My CFO doesn't really like saying, "Oh, I'm 95% confident that this is the right number." So, but things do like I said, like how many users visited Keisha's page or things like that. Most of the time, you know, 95%. You know, 90. What was that? 98.37 is good enough. There's also some new sketches out there called data sketches, and these sketches are meant to harness the power of sketches, but to be able to use them for more rather than just simple counts and things like that, being able to do differentials and overlaps and things like that. So Theta is really good at, you know, doing, like, let's say I want to do a funnel analysis or things like that. I can use a sketch to do an overlap between sets. So I can say, you know, how many users went to Keisha, but not Justin Bieber, right? It's good for retention analysis. It's useful for order independent funnel analysis, things like that, where HLL sketches wouldn't really be, you know, wouldn't serve that purpose. Because of the additional functionality that they provide, they are larger. They could use up to 30x more memory. They are a little bit slightly slower than HLLs, you know, but use HLLs when you don't need intersection and difference calculations if you're just doing simple sketches, right? The nice thing about this is all of these sketches is the Druid provides SQL functions for those. So rather than having to code your complex intersections and things like that, Druid has taken away that complexity and built in functions. So I can just say, what's my intersect between theta 1 and theta 2, right? Again, approximations and confidence intervals are good to know. So confidence intervals for you know, a size of 16,384 is about 0.81. So that would be the error rate that you would experience on average if you use data sketches. But those are tunable. So you could get, you know, you can increase the size and bring down your, bring up your confidence interval from that point. Quantiles, same thing, still uses sketches, useful for analyzing the distribution of numeric values. So this is good for things like latency, if I'm doing network, or you know, things like that, where I'm trying to understand quantiles or quartiles or things like that. What parts of my data fell within those buckets, and so we have 4 implementations of these. So one is a histogram, data sketches, tdigest, and moment. I don't know the difference between those, but we do have 4 of them. These are all part of the core extension, so these are not contributed. These are all available inside of the Druid platform. We do extensive testing on them to make sure that they're providing the right performance, and they're integrated correctly and in such a way that they're easy to use for the end users. Yeah.
Sorry, John.
Yeah.
Just to let you know, we don't have enough time.
Okay.
Yeah.
Well, the good part is there's that was it.
That's very good.
Yeah. So long story short, to round up with Aladdin, sketches are very, very powerful. Very, very powerful. Phenomenal cosmic powers in any bitty storage space. And that is last part. How do we query data? I think I alluded to this earlier, but there's a couple of different APIs. So if you like writing JSON and having full control over the query pattern, you can do that. Or if you want to use SQL, you can send SQL to the system and have it answer you.
Thanks, John. Lee had a question.
Yeah, absolutely.
Lee, you can go ahead. I'm just telling you Lee now with your last name because you both got very similar name, John. You have a question?
Okay.
Yeah.
Thanks. Yeah. You mentioned multiple times about the river. I'm trying to understand the data lake river. I know the data lake. I know the warehouse. So I know the data lake house. And also now, because the data lake could become data swamp, we have the data lake.
Yep.
Now I'm not sure about your river.
Yeah, so the data river is more of a concept about if there are streams of data that are very valuable, like let's say I'm doing a rollout and I want to know how my software rollout is doing, especially for a commerce platform. If I want to know immediately how my sales are performing on that new version and compare that to old versions, that would be something like you would egress from the application side directly onto Kafka, and then directly into something like Druid. So that would be a data river. Whereas like your operational logs and telemetry logs and things like that, you probably don't need to know those right away. So you could put those directly into the data lake. But sales numbers, revenue numbers coming, the order numbers, things like that, that would be a data river type of data set.
What about the user web traffic? That type of data?
Yeah, you could definitely do that. So like Apache web logs, things like that, to see, let's say you have a new page going live or something like that, and you want to know how that's performing. Absolutely, you could take your web logs and put those into Kafka and then directly into Druid.
So that will be its own river, or?
Yep. Yeah, it could. Yeah, it could be its own river. They could live. Well, I mean, you could merge them into the same river, and just do filtering on those and say like read off the same Kafka topkit. But say for this data set, I only want the revenue data, and this data set, I only want the web logs data, and then bifurcate those off of, into their own data sets.
All right, thank you.
Yeah, so you could have lots of little tributaries, or you could have one giant Mississippi River.
That was good. If anyone doesn't have any question, we would like to close the session here today. Thank you so much, John. It's a lot to learn. It is a great learning session, really. And thank you so much, everyone who have joined. John, I believe you're gonna hand over this slide to me. You can send it to the email, and then I can distribute to all the members who joined today. Yeah, yeah, thank you so much.
All right, thanks for the Dipankar. Appreciate it.
Yeah,
and
thank you.
It's great. Thank you, everybody, for taking your time and your evening to spend it with us. We appreciate it.
Thank you.
Right.
Thank you, John.
Thanks.
Thank you, Dipankar.
Yeah.
Okay. Bye.
Bye.